you really want to learn this thing. It's completely voluntary, but if you want to do it, come to me anytime to discuss them. If you have any questions, and of course, feel free to ignore them. It's not mandatory. Okay, so here is my motivation, and this is really, I guess, we are all here and we share the same sentiment. These are really exciting times. Like, so much happened over the last 5 or 10 years. For the first time in basically forever, we have access to quantum devices, quantum architectures that can host approximately hundreds or even more qubits. This has never existed before. When I was young, people were proud when they had 6 or 7 qubits. Now we have 100. But these things don't work in isolation. That's the entire idea. The idea of building a quantum computing architecture is to compute in a fundamentally different route. This is what Fernando mentioned. But this comes with problems. Fernando mentioned noise resilience and noise resistance, which is arguably the biggest problem. But on a fundamental level, another problem that is really annoying is that the result of a quantum computation is not provided to us in a machine or human-readable form. It's not a bit string. It's encoded within fragile correlations between the qubits. And so it's actually a non-trivial task on how to access them. We have to perform measurements, and measurements are destructive. So yes, we can perform a measurement, we get data, but then we destroy the system, which means that we have to rerun the entire quantum computation again from scratch to get another state to measure it again and repeat and repeat. And this is a really serious bottleneck, because it includes, in whatever we want to do with these devices, an additional loop of state preparation. And in a quantum computation, state preparation means you run the entire algorithm. And this is a serious bottleneck that has to do with the measurement problem, with wave function collapse. And there's really fundamental issues. And if we use the techniques we are used to, that we learned in school and university, then we will irrevocably see an exponential bottleneck. If you have n qubits, the cost of perfect state tomography, of perfect reconstruction, scales exponentially the number of qubits. For 3 to 10 qubits, this is not such a big deal, because 2 to the 10 is 1024. That's not a scary number yet. 100, 2 to the 100, we don't have enough, I think, time on Earth remaining to try to resolve all these individual. So we really need new ideas. And I hope that you can see, and you're with me, that any type of progress in this readout problem will help us coupling a quantum device more efficiently to a classical computer or worse. And this will boost up any type of variation on quantum algorithm, for instance, or really any situation where we want to use a quantum device to compute something. And this new approaches on how to deal with this readout problem, how to overcome this serious bottleneck, is exactly the content of this talk. And I want to convey some, once you think about it and adopt the change of perspective, not even very difficult ideas on how to do that. Okay? And the general setup on how we achieve that will be to really take resource costs seriously. Like, we're trying, and this comes in many forms. One of the resources is how often do we have to repeat our quantum computation to generate states that we can measure. This is the sample complexity, an important resource. Another resource, which is now becoming relevant, is the cost of storing the measurement outcomes. If I do continuous measurements on 100 qubits, I wouldn't probably be able to store the measurement. So we also have to take into account this. And finally, we also have to think about the runtime in order to process the data. How much classical computing time do we need in order to compute the things we are after? These are all things that matter, and I hope you're with me that these will all scale in the number of qubits if we go to larger system sizes. And if we have an overflow error in any one of them, we're kind of in a pickle. So we really want to come up with a framework that keeps all these resources as low as possible, and this is maybe the unique point, still comes with rigorous performance guarantees that gives us some confidence that they work. Because a really difficult thing for me, when you work with actual quantum computers, is how do you show that your idea actually works? I don't have access to a 100 qubit super quantum computer to check it, and numerical simulations get me maybe to 12 qubits. So So I think really rigorous mathematical results are helpful in this regime because they give us the credibility of mathematics. And maybe if you come up with a technique that can be underlined with rigorous performance guarantees, maybe this is more convincing and will actually work in practice once my waiting time is over and I get my quantum. Okay, so this is the general setup. And the overall rule of thumb, and you will see later why, is that we always think about a quantum system of interest. This can be an arbitrary state. For me, this is typically the final state of a quantum computation with n qubits. The measurement stage, where we make the quantum classical transition, and then something we can do before the measurement, maybe some evolution, maybe some rotation to learn something new, as well as a powerful classical computer which we use for storage and analyzing the data. And so this is the setup I consider. Prepare state, maybe apply a simple rotation, measure, and then do classical co-processing to predict many interesting properties that you as physicists might all know. For example, fidelities, entanglement entropies, local observables, or Hamiltonian. Okay? Are there any questions or comments at this point? So now, here is the maybe boring part I already announced. I want to really take the most basic example I can think of, estimating Pauli observables, and put them into this framework and really analyze what the resource costs. And we'll take it from there and then scale it up to many qubits. And I understand that this might be boring for many of you, but I chose to kind of like highlight this different point of view and this way of proving and thinking about things maybe at the most easiest example. So how do you estimate a single Pauli observable? So here is like a gate picture or a pictogram of what I think. This is an unknown semi-qubit state. This is a computational Z-basis measurement or computational basis measurement. And this is what we call today a unitary gate, a unitary operation that you can apply to the state before you measure. And if you perform this measurement, you get a bit. You get 0 or 1 bit. You don't get the expectation value of the Pauli matrix. You get a random bit. And the information about the density matrix is not encoded in the bit we get, but the underlying probability distribution. So this is just Born's rule and tells you the probability of measuring 0 has something to do with the first diagonal entry in the rotated density matrix. The second is this one. How would you use such a setup? How would you program it to estimate the observable that you physicists might write as this, which is the trace of the density matrix times the Pauli Z matrix if Pauli Z is that? How would you do it?
Well, I guess you have to perform various measurements and then find the frequency of the desired observable.
Do I have to do different types of measurements?
No, the same one. No.
Okay, very good. That's the correct answer, and I like the frequencies because that's directly translated to probabilities, which are kind of these things that we can see, right? Here's like one formal way of showing, writing down an estimator that is efficient in all the resources we've seen so far, and it better be because this is single qubit. So I rewrite the expectation value of the Pauli Z matrix as probability 0 row 0 minus 1 row 1. I'm just inserting this into the matrix. Now, I realize that if I'm really interested in diagonal entries of the density matrix, I better not rotate at all. So I don't do anything, any rotation. I apply the identity here because I'm measuring in the right places to begin with. If this were the x basis, I would rotate. And this is now nothing but the probability of obtaining 1 minus the probability 0 minus the probability of obtaining 1, which is exactly what you set, and now we can approximate this with frequencies, right? I want to do an intermediate step to make sure that this remains scalable and efficient. This is just like a reformulation of the identity. I can write it as -1 to the power of the outcome I've seen. Okay? And if I write it in this way, and know a bit about probability theory, then this defines the expectation value of the function. So this is the same as the expectation value of -1 to the power of the bit I received, averaged over the underlying probability distribution given by the set. Okay? And this is what we approximate. Because this is now an actual mathematical expectation value. And in order to approximate it, I can build an empirical average. I can do many, many independent samples of this random bit and take the average of this function over all the instances I've seen. Okay? I think this is formally equivalent to what you said. I just wrote it down in a different. But the idea is really, you first find the right basis, then you perform a single shot measurement, you take it very seriously that this is a random bit, and you find the right function to compute on that bit that would give you the observable you care about if I average over all possible instances, and then I approximate this true expectation value by averaging empirical samples that I can generalize by repeating the measurement all over again on new copies. Okay? So far so good. I think this is a strategy that you all know, just written maybe in a slightly different way, to make sure that this function is easy to compute, that it will be scalable, and so on. And one reason why this works is that the central limit theorem tells us that such empirical averages, frequencies as you call them, are guaranteed to converge to the true expectation value in the limit of infinitely many samples. This is what the central limit theorem tells you. It's a bit annoying because it doesn't tell you when this happens. And this is one of the problems I want to address. We will find techniques to prove how large this T has to be so that this is approximately true. Because the CLT doesn't give you. It just tells you asymptotic. Never says it's asymptotic. Okay? Much more on that later. This is really like the main message I want to convey today. And now, bit coarse-grained, if I have a single qubit state, you don't know what it is, but you can press a button to produce it, then me and you together, we came up with a recipe on how to estimate this in this setting with efficient classical post-processing and efficient memory. And the recipe is, we do nothing in the unitary stage because we anyway measure already the correct basis. We perform many experiment shots independently. These will give us bits, that this is a bit of a cumbersome notation that we'll need to generalize it to many qubits later, but this is just a different bits that we get. And then we take this bit and compute a very simple function, -1 to the bit value, and average it over all the shot bits. Okay? Now, very difficult question. Can you help me? How will we estimate 40x? Is this similar or is this a completely different story? Or can I do a simple trick to reduce the task of estimating poly x to the task of estimating poly z, which we just really understood? I can see something like this. Are you proposing to rotate poly x into poly z? Excellent. This is exactly what we do. And this is achieved by applying a Hadamard gate, a native gate on a quantum computer. So this is one of the cheapest gates you can use on a quantum computer. But if you do that, you basically commute the z basis into the x basis, and then you're back to square one. You kind of like just rotated your density matrix, and you can do the same estimation I told you before. You will get a bit. The right expectation value is encoded in -1 to that bit, and you do the same type of empirical averaging. You approximate an expectation value by a collection or an average of point losses. And yes, the formula for the rotated observable for poly x looks exactly the same as for poly z because we rotate the density matrix. And now, the first homework for you, which shouldn't take you too long, is think hard about how you would do poly y. Is it fundamentally different from poly z or x, or is there a similar trick? And if there's a similar trick, what's the rotation? Okay? Shouldn't be too difficult. And something that will be nasty later on, and we will use randomness as kind of like cheating, is to just emphasize something that you might know. that Pauli X, Y, and Z as operators don't commute, and that means that we can't jointly measure them. And that means if I'm now interested in X, Y, and Z, I have to make a choice with my rotations. And depending on what I'm doing, I'm either learning X, I'm either learning Y, or either learning Z, or something in between, but then I don't learn quite as much for the other two. Okay? So this is really a choice. And the easiest thing is to choose X, Y, Z and measure them sequentially, but it's not possible to cook up a good experiment that tells you much about both. Okay? So this is really an exclusive choice to get. Now, I really want to take this reformulation that we did in terms as an empirical average of a simple function in order to prove how many shots we need to get a good approximation. So that we don't have to rely on this annoying central limit theorem when nobody knows when asymptotics kicks in. And just as a reminder, let's do the Pauli Z case again, the easiest case so we don't rotate. How do we approximate the Z observable? We take independent repetitions, get random bits. For each random bit, we compute -1 to the power of this random bit, and then we form an average. This is our estimator. And the question now is, how large does T have to be so that this approximation is as close as we want it to be to the true expectation value? And the central limit theorem, I told you already about that, tells you that this will happen at some point, but it does never tell you when. So you never know how much money to spend. So let's do something else. And here is the first theorem of this lecture, which is actually a consequence of analyzing point process and doing relatively basic probability theory. I claim that the number of repetitions you need, the shot cost, scales inverse quadratically in the desired accuracy. If you want to get error bars of the size of 10 to the minus 3, it's going to scale to 10 to the minus 6. It will scale logarithmically in the confidence, the probability of failure you're willing to tolerate, and nothing else. Most importantly, this is an actual number that you can compute, which is strictly smaller than infinity, what the CLT would tell you. And the same, I hope you're not surprised, holds for estimating the Pauli X matrix, if I do the Hadamard rotation, and if I do the Pauli, this should be a Pauli Y, if I do the Y rotation. I could come up with another statements for that. So how do I prove something like this? This is a consequence of what in probability theory is called tail bounds or concentration inequalities. These are quantitative versions of the central limit theorem that basically tell you how often you have to toss a coin until you know the bias for a certain thing. And they are strongest in this setting. So we now assume that we have a collection of T random variables. Remember that the outcome, the single shot outcomes of our measurements are random variables. Quantum mechanics is a probabilistic theory. And these random variables have to be independent. That means there's no macrobianity between them, they have to be statistically independent. Quantum mechanics gives us that for free. Because with the measurement collapse, we have to restart the entire process, which means that the new bit will be independent from the old one. This is really a powerful resource that quantum computing and quantum technology actually gives us for free. Each sample is statistically independent. And another addition that you need for this concentration inequality is an assumption that all these random variables are within an interval, so that they're bounded. They don't become arbitrarily large. And if this is the case, Preskill inequality tells you that for any error threshold you think about, the empirical average, the sum of all these random variables divided by their number, in absolute value, is larger than epsilon away from the expectation value. The true expectation value of these random numbers is exponentially small. It's really like if you think about a Gaussian, it tells you you're far out and like the probability of this happening is super tiny. And if you take this, which is actually not that difficult to prove, we can just apply it to our single qubit measurement problem, right? Because as a proof sketch, our random variables are -1 to the random bit we obtain. This is why I care about this reformulation. And this is a binary random number. This is either +1 or -1. This is as bounded as it gets. So it's really an interval -1, 1. Each of these random bits is independent, so the function is independent, And so I can straightforwardly apply this concentration inequality using the fact that I know that the expectation value of these guys is the observable I care about. This is what we proved for the last slide, right? And if we apply it, I can just rewrite estimator minus true expectation value is the same as this sum. I just pull out the sum in our empirical average. And now I just apply this Höfling inequality and I get, voila, an exponential concentration in the number of shots I do. And this is very, very good, because that means if you do more shots, the probability of being far away diminishes exponentially. This is really good. Okay? And it follows from one of the most fundamental and basic results in probability. And maybe this is not so surprising, because we only looked at estimating single qubit Pauli observables, and I guess we all believe that we don't have to spend infinite money on shots there. The remarkable thing I now want to show you is that this intuition generalizes to many qubits, and the scaling in the number of qubits might not be as bad as you think, because of these exponential concentrations. Are there questions or comments at this point? Yes?
I was just wondering if I misunderstood on the exercise. Is it the trace of Z row or is it Y?
No, this should be Y, sorry.
Ah, okay.
No. It can be C as well, but then I solved the exercise for you already. Thanks. And thanks for paying attention. Means a lot to the German elite. Okay, so this is kind of like a warm-up example. I'm sure that I told you things that you might have already known, but I hope I was successful in maybe changing your perspective a bit and sneaking in tools that you don't learn in quantum physics. And so let's push these techniques maybe to the limits and go to more qubits. Starting with a simple case and then kind of like generalizing to more difficult general cases. So let's start to estimate n-qubit Pauli observables, where you should think of n being a reasonable number. Let's say 100. Here is a general estimation protocol that is very feasible on today's quantum hardware. We have an unknown n-qubit quantum system. This could again be the result of our actual quantum computation, maybe on one of Fernando's devices. And this is the standard measurement setup in quantum computing. Computational basis measurements on individual qubits or Z-basis measurements. And in principle, quantum computing allows you to do arbitrary unitary rotations after the quantum system, after the state preparation and before the measurement. It's a bit similar to what you said. But in practice, this is not true, because most unitaries you want to implement are exponentially deep, and then you have problems with the 2-qubit error rates, and you can't implement them. So we cannot implement very, very interesting unitaries here, which is why I'm sticking to this tensor product, to this parallel application of single qubit gates. This is simple, native, and cheap in every quantum architecture, and it avoids the noisy 2-qubit gates that are a reason for error correction. So this is kind of a relatively general, kind of like a near-term friendly setup. And what you get now is not just one outcome bit, but you get n of them. And this is part of the reason why my notation looked overly complicated on the last slides. We now have n of these bits. And now, let's cook up an estimation strategy for Pauli Z terms. So for observables that only include single qubit Pauli Z matrices or identities, as a warm-up example. Here's my first question. You would write it probably as expectation value of Z on the first qubit and identity do nothing everywhere else. I would write it in this fashion. Pauli Z tensor n minus 1 times the identity, trace in a product with an estimation flow. How would you estimate that?
You make the same thing before, but more times for the same number of bits?
I do the same thing as before. I like that. And I really ignore qubits 2 to n completely, right? Because if I don't include them in my estimation process, it's the same as measuring them and forgetting them, which would correspond to the partial trace, which will give you the reduced density matrix on the first qubit, which is all we need to know to compute this particular estimation. If this was a bit quick, this observable only has a Z on the first term and nothing on the rest. So it only cares about the first qubit. And so it's effectively a single qubit problem. I want to just estimate policy on the first qubit, forgetting everything else. Well, here's an estimation technique that does it. From our previous discussion, you will not be surprised that if I just take the first random bit and forget everything else, and compute -1 to this random bit, and I take the average, I will get precisely this single qubit policy expectation value. And so my estimator for this structured Z term is really the same thing I did before. But now I had n random bits to begin with, I only used the first one. Let's amp up the difficulty a bit. How would you do this? I'm giving you the answer. This is kind of like a product of two Pauli matrices. And if we do a measurement, the collapse of the wave function breaks all possible correlations between the qubits. And so I can make a product ansatz for these two qubits. And because the product of exponentials is the exponential of the sum, if you really want to implement this, you would take -1 to the first random bit you saw plus the second random bit you saw. And if you average this, it's an easy exercise. You will really see that this is the same as Pauli Z on the first two qubits and nothing on the other qubits. Okay? Now, I don't want to be too boring. Let's amp up the difficulty. How would we estimate magnetization like Z everywhere?
The same thing as we have with the summation of all the S1.
Yes, very good. Thanks. He said what I wrote. And I hope you see the pattern. We now really have n different bits. Collapse of the wave functions decouples. We can make a product ansatz. And if we really are interested in all the Z terms, we add up all the possible bits in the parity. And now you can see a pattern. If I asked you about the second to last and last one, you would know how to construct an estimator. Right? And once you know what the correct expectation value is, you can really always do infinity averaging by doing now t repetitions of the entire thing. And this gives us additional power because each measurement now gives us n different random bits. So the measurement is more expressive. For n qubits, we always get n bits, and so we can learn more. But the overall cost, the number of repetitions still stays the same. Okay? One important thing that will become really crucial in the last part is this approach really only works if we measure in the C basis everywhere. And I hope this is not surprising for you, that if I were to measure, for example, in the X basis on the last qubit, then this wouldn't give me information about the C direction of the last qubit, because I went into an orthogonal direction. However, and this will be our trick, it doesn't affect, this unitary doesn't matter at all if I'm only interested in observables on these qubits. Because if I don't use them for the estimation, it doesn't matter in which basis I measure them. For example, here, if I only estimate the first qubit, it doesn't matter what unitary was the second qubit, third qubit, and fifth qubit. Only the first qubit counts. Okay? This will be structure that we will use later. Now, I hope you're with me that there are 2 to the n, exponentially many such structured sequences. I can always choose identity or Z on a given qubit. There's 2 to the n options. And we can use the same measurement setup to estimate all of them. I wrote down the estimators. And this makes also sense from a physical perspective because all these observables commute. So I can jointly measure them, but here we have a concrete analysis. But this is actually the thing I want to tackle next. What is the cost of estimating, for example, all these 2 to the n different Z terms with the same measurement data? Is this going to be exponential in the number of qubits because we are interested in exponentially many things? Or maybe can we save? Okay? And just before we go there, just very quickly, I hope you're not surprised that I could have told you the same story about only X measurements and with different rotation here, or only Y measurements. This is the second homework. Do the same analysis I did before for terms that either contain a Pauli Y or the identity matrix. Same setup. But now, let's kind of like push our probability theory guarantees, these Höfting ideas, to the limit and try to compute numbers of the actual short cost it takes us to compute these 2 to the n guys. They commute, like a not yet general case, but maybe it's interesting, right? Because we could see a curse of dimensionality here if we are not careful. So here is the setup. I'm not necessarily looking at all possible combinations, but only capital L mainly. So what this means is a lot of notation, but think about L, capital L, a large number of distinct polymatrices that are tensor products of only poly-zero identity, like in the first case. And capital L can be anything between 1, I'm just interested in 1 polyobservable, to 2 to the n, the maximum number of different subtypes. And we already know the estimators, and I'm streamlining the presentation here. So instead of really writing all these parity sums that we together came up with, I write this as an inner product of the bit string vector with the indicator vector for your observable that tells you where poly Z is and where it's not. So this would be 0 if you have an identity component, that means you don't care about the system, it doesn't appear, and it would be 1 if the observable here is interesting, if it has a poly Z, and so you keep the associated bit in the exponent. Okay, this is just a more streamlined notation of the things, of the pattern we discovered before. Another question is, how large must T be? Yes?
That index, the Doppler index in Sn on the last one should be T, or is somehow else?
Yes, that should be T. You have eagle eyes. Thank you. So last one should be T, because it's kind of like a teeth shot for the alpha cell. How large must T be? Well, the central limit theorem tells us asymptotically it will converge. But when does asymptotics kick in? When you're in 2 to the 100 dimensions. Okay? Well, there's several answers, and it has something to do on how we deal with the data. Here's maybe the conservative approach, which I call the sequential answer. If we're interested in L polyobservables, I told you before how to estimate a single polyobservable. You could execute this protocol L times. Take data to estimate the first guy, take data, estimate the second guy, take data, estimate the third guy, and we proved before that for a single polyobservable, it's not that expensive. Okay? If you do that, you get a resource cost that scales linearly in the number of observables and the number of properties you care about. Is this good? Or can we do something better? Is this something you would do if I forced you to pay 10 reals or 10,000 reals for each shot? Would you really be so disciplined to do it 10,000 times only to estimate the first guy, and then do it 10,000 times again to estimate the second guy? Or would you use the same data more often? Well, maybe you would parallelize, right? You would use the same data to predict all these observables, because you can use the same data to predict all these observables. But now you can ask yourselves, how much more expensive does this become? How many more shots do I need in order to make sure that this correlated estimator, these correlated random numbers, all converge correctly? And the answer I want to convey to you is that this overhead is super small. It only scales logarithmically in the number of observables. So instead of the sequential answer where you would pay a linear price, you pay a logarithmical price. This is an exponential improvement from linear to logarithmic. In particular, as a consequence, if you're interested in all 2 to the n poly Z terms, the number of shots you need scales only linearly in the number of qubits. So if at 100 qubits, it's 100 times more. That's extra cost, but that's extra cost we can afford. Okay? I'm going to prove that on the next slide. Here is a homework challenge, and maybe the most interesting homework I have for you. Do the same arguments we're doing now for poly observables, but for the 2 to the n different outcome probabilities of the density matrix when you measure the computation on the C basis. There's 2 to the n different bit strings, each is assigned with a certain probability. I'm now asking you, how would you estimate all of them doing measurements like this, and how many shots would you need? Okay? I'm going to put this exercise on the very last slide. But it's kind of like the same setup we do now, but for estimating probabilities. Here is kind of the main result of today, where I'm going to prove to you that if you use the same short data for all observables, the extra cost you pay is only logarithmic instead of linear. So here's the setup again. It's a bit notation heavy, I apologize, but I want to be really concrete. We have Z-type target observables. So observables that are either identity or poly-Z, that look like this, and we code them with these activation vectors, where we put a 1 whenever there's a poly-Z and a 0 whenever there's an identity. We have T outcome shots. So we measured in the computational basis T time, and each of them gives us a bit string of size n. 0, 1 for each qubit. And we know how to estimate all observables. We just form this -1 to the power of this inner product. This is the thing we developed. And we can do that for all these n different terms. And if you're ignorant, we can use the same data to compute all of them in parallel on different machines to also save resource cost. How many measurements do I need in order to make sure that this works? Because I'm reusing data. This is maybe something that the experimentalists among you know, that it is a bit equally dangerous. The answer is this logarithm that I ever mentioned. If you take these many shots with these assumptions, you ensure that the maximum deviation in absolute value from the true targets, from two observables, is always smaller or equal than epsilon. And this is really almost the same scaling I showed you as for the single qubit case, right? There's only a log alpha. So how does this work? It's actually not so difficult. In the first step of the proof, I forget that I'm interested in very many different observables. I just pick my favorite one of them, like the index L, from 1 to L, and just look at this. And there, I know what to do. Because this estimator, this empirical estimator, is an independent average, these are independent shots, of a random number that is either +1 or -1. So it's bounded, right? So our old friend Preskill tells us that the probability of a single deviation is bounded by 2 times exponential in the number of shots. So the probability of getting a single deviation diminishes exponentially as we increase the number of shots. Okay? The problem is that this is only true for a single observable, and now I'm trying to sell you L highly correlated estimators, which looks dangerous. But is it really dangerous? And the answer is not really. Because another fundamental result from probability theory is called the union bound or Boole's inequality, and it tells you that the probability of a union of two events is bounded by the sum of the probabilities. So the probability of my paper getting rejected at QAP or getting rejected at TQC is smaller or equal than the probability of getting rejected at QAP plus the probability of getting rejected at TQC. And it's typically proven with these Venn diagrams. Okay? And maybe, and this is true although the random variables can be very correlated, if my paper is shitty and it gets rejected at QAP, chances are higher that it gets rejected at TQC as well. This doesn't matter for this type of fundamental inequality. Okay? And so we're going to use that, because this is true regardless of the underlying relations. And now, I just look at the probability that the maximum deviation of any of my estimators is larger than epsilon. And if you think a bit, this means that either the first estimator is far away, or the second estimator is far away, or the third estimator is far away, or the fourth estimator is far away, and so on. So this is really a big OR of different deviation events. And now I use this union bound, the Boole's inequality, to replace this big union with the sum over the probabilities. Okay? This I can do although all these events are highly correlated. I can't do this. And now, I just insert my good friend Höfti. And I do it L times, once for each of these probabilities. They are now separable. They are now separate. And what I get is an extra factor of L, because I need L of these bounds. But each bound is exponential in T. Okay? And I use this exponential in T to kill this linear L overhead with this log L. Because x of log is 1 over with a minus sign. And so these very elementary techniques actually tell you that they can reuse data and do parallel estimation of exponentially many polio variables that are all in the same basis. But the extra pay you have to do is only logarithmic in the number of targets. In this case, it's linear. Are there any questions or comments at this point? I hope I have been succeeding by showing you that relatively elementary tricks can be surprising when you look at scaling issues in quantum computing. I really find this remarkable, and I hope that at least some of you agree with me, because naively I would have expected an exponential cost if you want to estimate exponentially. So here is really the first main lesson learned. We can use the same shot data for to predict very many poly Z observables all in parallel. And this is very good for all computational resources, because our setup is easy. Yes?
Sorry, would you mind to go back to one slide? So, on the result, it's 2L.
Sorry.
I'm being very stupid, but I think this, your results, like starting with 2L, that's the sequential one?
Yes.
Can you push it to parallel?
Yes, I did it here. Kind of like the trick is this is true for any sequential estimation.
Right.
This is just true for probability of a single guy deviating, not caring about anybody else.
Right.
And here I'm interested in a correlated guy, one of them deviating, but I use this union bound to replace the probability that at least one of them is bad by the sum over the individual probabilities of being bad. And in this step, I remove all the correlations with a simple upper bound. And I have to pay because the sum of the probabilities often can become larger than 1.
Yeah. Okay.
But this is exponentially small.
Yeah, I was just wondering if you would have the L outside of the exponential thing there. Yeah.
Yes,
Yeah.
because it's a sum over L terms.
Yes.
And I use this exponential for each of them.
Yes, thanks so much.
Thanks. I think this was helpful for all of us. But I'm confident. I did this approximately 100 times already. My career would be dead if this were wrong. Okay. So far so good, but I guess you all agree with me that so far we only solve easy problems. Because we have this restriction that all the observables we cared about are either identity or Z operators, which means that they all commute, and then we can find one measurement setting to rule them all. This is not the case in real life. Typically, you are interested in maybe poly observables that have X, Y, and Z components, and if they happen on the same qubit, you're in trouble. Because remember, you have to choose to either measure X, Y, or Z, but you can't have all of them. So what do we do here? Now I want to say the same setting, but now the general task is not to approximate structured poly observables that all commute, but a general selection of arbitrary poly observables. So this will allow every qubit we allow identity X, Y, or Z. This is the general poly estimation problem. And the setup I want to use is now a bit more general, because now I'm going to need the freedom of doing single qubit rotations to like convert from Z to X to Y. Okay? So now we have this general setup where in each repetition we can choose a different set of unitaries to apply here, get the shot and store it. So the measurement data is now actually a string that is meaningful in two ways. We first store the types of rotations we did to know which poly observables are compatible, and the big string that stores the random information. And we do that again t times. And now the question is, how often do we have to run this to estimate a general collection of poly observables that may or may not commute? And the naive strategy is, well, let's do it one after the other, sequentially. 1 over epsilon squared times the first, 1 over epsilon squared times the second. If you do that, the number of shots scales linearly in the number of observables, and inverse quadratic linear is. We've seen that already. You can always do that because you don't even care about doing something smart. I call it wasteful in the slides, I would call it stupid in a talk. Here is the optimal strategy that some of you might have heard. This structured Pauli estimation thing we did at the example of Z-basis measurements, identity or Z, is actually true for any collection of compatible Pauli observables. It doesn't really matter whether it's X, Y, or Z, it's only matter that it's kind of like collectively the same. And so you can look through your section of many observables and try to group them into compatible sets that all commute and can be jointly estimated. This is a difficult pre-processing problem, but if you find it, you've divided up this general problem into an optimal number of simple problems that we have already solved. And then you do that sequentially because you have to, because Pauli matrices are incompatible. If you do that, the number of shots you need scales linearly in the number of groups you need. And this is optimal. The problem is finding the minimum numbers of groups is empty hard. This means that it's computationally very, very difficult, and we don't expect general solutions if we go to larger and larger problem sizes. These problems are harder than factoring, and at least as hard as traveling salesman, for instance. So maybe you don't want to rely your readout protocol on solving P versus NP. Okay? Here is the solution or strategy that Robert Huang, John Preskill, and myself came up with, which is kind of cheating. We do a randomized strategy. And which means we do denial of service. We don't even look at the observables, and we just choose each of these unitaries independently at random. There are three interesting options C, Y, or X. We flip a coin and choose one of them uniformly at random. And we do it for each of these qubits. Okay? And then our hope is that if we do this often enough, by sheer dumb luck, we will find measurement setups that are compatible with these observables. And then we can do everything in efficient classical post-processing. It's really kind of like denial of service, randomizing, measure first, ask questions later. Yes?
I don't know if it's in your homework, but it may be a good question why 3 and not 4 options.
Oh, because the identity matrix?
I know the answer, but I don't know if it's a homework.
Okay, he just gave you a new homework question. Very good. I'm not going to answer it, but I guess the two of us are available for discussions if interested students want to solve it and discuss it. Thank you. And what we get is something that interpolates between the two extremes, and we get a scaling that is logarithmically in the number of guys we're interested in. I'm sorry, this is a typo, this epsilon squared should be the confidence delta, inverse probability in epsilon squared, and it scales exponentially, in the weight. This is the number of non-identity terms in a Pauli observable. So if you have two local observables, this is 3 to the 2. If you have a global Pauli string, like in Fernando's error correcting protocols, this is horrible. This is 3 to the n, this is exponentially expensive. Okay? And the weight is just the maximum number of non-identity terms in each of these observables. It's more or less the physical locality. What I'm saying is, with randomization and denial of service, you can get completely away with it, with very good scaling, as long as the observables you care about are local and don't address all the qubits. And the reason for this is really kind of gambling and hoping for sheer dumb luck. Suppose that our target observable is 3 local. It's maybe a y here, it's an x here, it's an x here, then another target observable 2 local, it's a z here, it's a y here, and so on. And the third one is again 2 local. And now I really do complete randomization. Like in each stage, I choose each of these single qubit gates uniformly at random. Then the probability of getting the right basis for this guy is what? It's 1/3, right? Not bad. That's an odd I would play. The probability of also hitting this guy independently is again 1/3. Probability of hitting this guy and this guy is 1/3 squared, 1/3 to the squared. And for the third one, we get 1/3 to the cube power. 1/3 over the weight. Okay? You see that these odds are not great. They diminish exponentially as the Pauli observables become larger. But if we have local terms, it's not that bad. These are odds I would play. And then just sample a bit more often to make sure that I hit these guys. And the thing that really makes this work is that every time you do a randomized measurement and you get a shot, you play the game for all observables. Because you could use this shot data for all L guys, right? So you're not only playing it once, but you might succeed more often than once, or if you fail at one, you might succeed at the other. Okay? And this is the general reason why our performance guarantee scales in a weight, because the probability of hitting them with dumb luck diminishes exponentially in the weight of the observable, and so we have to counterweigh that. But other than that, the arguments we did so far go through completely, and you again get a logarithmic scaling in the number of things. Here is maybe a bit more intuition for a proof strategy. I won't do the proof today, because we will revisit the same problem, not from the Heisenberg observable perspective, but from the state perspective on Thursday, where I will prove this to you in a different, kind of like in a different setting. But here's the intuition. And I don't know if you still watch The Simpsons, but like in one of my favorite episodes, and it was actually a source of inspiration, Mr. Burns is very proud and shows Homer a chamber where there's 1,000 monkeys working on 1,000 typewriters because they will write the best novel that ever was. The argument is the probability of them not doing it is strictly smaller than one, so one of them will do it at some point. Okay? So really just randomness. And in our observable polygroup in question, it's a bit similar. We don't try to think hard, we put a monkey with 3 buttons on each of the qubits, betting on the fact that he can't be wrong all the time. Okay? And you can see it here, kind of like if our poly observable is like this, it only affects the middle qubits and maybe in a certain color, which indicates maybe poly X, then in order to reproduce this, we only have to get lucky here and here. And it doesn't matter where the rest is, because this doesn't matter for our estimation at all. On the contrary, if we had another guy that maybe was supported here, we would play the same game, and if it were compatible here as well, we could use the same shots for both. And so really, every randomized measurement allows us to win L different times. And the probability of hitting a weight W poly is 1/3 to the weight. And so with these odds, you expect to expand or pay an extra 3 to the weight factor to compensate these lower odds. But that's all there is. Once you've done that, you can be sure that you have enough data for all of these guys, and you effectively have a structured poly estimation problem. Exactly the problem we treated already, and then we get this additional scaling. And previous conversion guarantees that we derived today, take it from me. Okay? This is not a complete proof. A complete proof is a homework. But I promise you that we will derive an equivalent result next time when we talk about classical shadows. Am I out of time?
No, we still have 15 minutes.
Okay. Is there questions or comments at this point? I really encourage you to try to prove that by yourself. And come to me if you're interested in like hints or want to kind of like discuss it a bit further if you have a solution.
So one question. So you do this randomized measurements, but then in the end, to really estimate your variables, wouldn't you have to know K, like to know that which observables are compatible with this string that you generated in order to really get this package?
Yes, excellent question. How expensive is that?
Yeah, it's NP hard.
No. In order to check if a single measurement setup is compatible, I have to check n boxes. This is linear.
Okay.
It's a completely different thing. If I want to like be smart and try to group the poly observables into relatable collections that I can jointly measure, this is a hard problem because it's a bit like NetSec. But here I'm not doing this. I'm just tossing the coin and evaluating linear time if I win for a given observable. And I do this for all observables in parallel. So this is the opposite of an APR problem. This is kind of like as parallelizable and as efficient as it can hope for. You see? But thanks. I'm sure this helped a lot to clarify. Are there more questions or comments? Yes.
So in this method used to randomize the measurements you want to do, it kind of seems to me that it will work fine if you have too little measurements you want to do. In that case, for example, that's brown, you just choose true, and the others are irrelevant for what you random. But if you want a specific sequence that involves many of the output states, it will be very difficult to use that, right?
Yes, but this is kind of like what we say. The number increases exponentially in the number of non-identity polygons. So the more colors you put there, the more expensive it will get, as it should. I think this is what you're saying, right?
Yeah.
This is the exponential factor here.
Can I add something? Because like if you want a specific screen, then it goes with log L. But now the point, if you have many screens and you don't know which one you want to test at a given point, then it goes with this way. But if you want a specific one, then it's the former result.
Thank you. Okay, now, thankfully, I'm done with the dry, mathy computer science part. Thanks for suffering through with me. Let's now use what we've learned and try to show that it can make a difference in near-term quantum computing, okay? And one of the characteristic examples, which is very popular these days because we can do it on our noisy devices, are variational quantum eigensolvers, hybrid quantum classical approaches in order to solve problems in material science or quantum computing or maybe even combinatorial optimization. These are not rigorous algorithms. They are heuristics and we're excited because we can try them, and sometimes they work better than we would expect, and often they work worse than we hope. I'm not going to make rigorous statements about the general framework, but let's see how our insights from today can speed up any type of equilibrium. Okay? So here is kind of like the general setup in variational quantum algorithms. There we really envision small-scale noisy quantum computers of today, comprised of maybe 20 to a couple of hundred qubits, as a co-processing unit. A special purpose computing unit, a bit like a graphic card, that gets very, very specific computing instructions from a larger computer, executes them, provides feedback so that the classical computer does an update. And in variational quantum eigensolvers, this is envisioned to minimize Hamiltonians, to find ground state energies and ground state wave functions. Because typically your target is a Hamiltonian, and then you make a variational ansatz on your quantum computer. So instead of doing DMRG or maybe some DFT ansatz, you really have a way of starting in a simple state and then applying Canyon gates as well as parametrizable gates to create an ansatz wave function. And then you perform measurements on that wave function in order to determine the energy, the Hamiltonian, and maybe even its gradient. And this allows you to make adjustments to your parameter to lower the energy, and maybe you get a smaller upper bound to the ground state energy than a classical method. Okay, but here you really outsource to the quantum computer, prepare a certain state, and then estimate typically the energy of the Hamiltonian. And maybe some finite differences or something that tells you something about the gradient. Okay? And you can see that you can really view this as a state preparation setting, where the parameters are put in and then a state is prepared, plus a measurement stage that is intended to estimate typically the expectation value of a local Hamiltonian, like the one depicted here. Okay? So many times these Hamiltonians are structured and they are sums of local terms. So here I changed notation a bit, I apologize, but this X subject J means there's a poly X on this J qubit and nowhere else. And xj plus 1 means there's an X on the J plus first qubit and nowhere else. So this is a two local term. Okay? This is a two local term in Y, this is a one local term, and these are two local terms. Now this is a particular Hamiltonian that you get if you want to simulate one-dimensional quantum electrodynamics via the Lenzi-Schwinger model in a variational quantum eigensolver. Please don't ask me questions what that means. Peter Zoller explained it to me like that, I'm repeating it like a parrot. Ask somebody else. Interest in quantum electrodynamics in a V2 year. This is the Hamiltonian. How would you estimate this Hamiltonian? First of all, we maybe count the number of terms, right? There's n2 local x terms, n2 local y terms, n1 local z terms, and then there's order n squared of these 2 local z guys. But still, this is kind of like a very structured Hamiltonian, right? If we take all of these x guys together, we can do x basis measurement to jointly estimate all of them, right? With a log n over n. Then we can do y basis measurements to jointly estimate all of these guys, again with a log n over n. Then we can do the same for z guys here and here, and we can do these together with a log n squared, which is 2 times log n over n. This is why logarithms are great. They eat polynomial functions. Okay? So estimating this Hamiltonian is not so difficult. It tells you kind of like by itself, just by looking at it, which bases you should measure. But what Zola and friends did in 2019, which I found kind of like very inspiring, is they didn't estimate the energy of their ansatz wave function, but the variance. In physics terms, I guess you write the variance like that. In question to the audience, why would anybody be interested in finding a zero solution to this variance equation?
You can find the limit for how small you can have the precision for your energy.
Yes. Or let me put it differently. I claim that this variance is always non-negative, and if it's zero, something interesting happens. Of what?
The energy of the
Ground state energy, yes. So if you have an eigenstate, the variance vanishes. And if you do such a variance minimization, this gives you the chance of not only approximating ground state energies and ground state wave functions, but low excited wave functions as well. And this is what they did. So they didn't want to solve the ground state problem, but they were interested in low energy eigenstates. And this is one way to do it. I think there's a question back here.
Just a quick question about the Hamiltonian. It's not clear to me, this J index is associated to what exactly?
Sorry, J should be K.
Okay.
Thank you. You shouldn't write slides on a pen. Okay, but this is actually something really interesting. They did it in 2019 in a Nature paper, and if you actually minimize the variance, you have another variational problem. And it allows you to not only do ground state problem solutions, but really find more general low energy eigenstates. The problem is, if you take the variance of this Hamiltonian, it becomes a beast. All this nice structure I told you about, where we could just eyeball it and see an optimal measurement pattern, it goes berserk. It's really nasty. I'm not giving it a number. It's like funny, but you have to square like all these terms, and then like you get these different correlation functions. You can see that. It's a huge sum when you square it. The only saving grace is that if you square it, what is the largest locality, what is the largest weight you can get? And the Hamiltonian that is comprised of 1 and 2 local terms are squared. How large can the locality become? No? 4. Right? I could find this guy, x1, x2, multiplied with set 3, set 4. But that's the worst that can happen.
The harder question is this 4 2 plus 2 or 2 times 2?
Another homework. Okay? But so, trust me, this is a monster, but it's 4 local. And this was our window of opportunity. Because remember, on the last slide, I showed you this randomized denial of service measurement protocol, where I showed you that the number of shots you need to estimate a lot of different terms, all terms in a 4 local Hamiltonian now, all without structure, scales logarithmically in the number of terms. So instead of polynomial in n, we get logarithmically in n, and exponentially in the locality. 3 to the locality. But 3 to the 4 is really not scary. I don't know, what is it? It's 27 times 27. Like order of 100 or a couple of hundreds. Okay? So with our randomized strategy, we are guaranteed to estimate or approximate all these terms with only logarithmic overhead, and the constant offset we pay is 3 to the 4th. That's not scary, and this is something you see in this plot. Kind of like here, this is a log plot, where if we increase the number of qubits, it tells you how the number of shots needs to increase in order to accurately resolve your current energy variance. And this is an important subroutine in each step of your operational quantum procedure. And a big part of DQE is that if your quantum coprocessors become larger, the number of terms in your Hamiltonians become larger, and you need more shots to resolve all of them. If you were to naively do it, you get such a curve in a log plot, which is a polynomial scale. And this is bad, especially if you were happy and then you can use the IBM Eagle device with 127 qubits, and suddenly you pay a polynomial factor in 127 every iteration of your DQE. This is bad. And the original authors of this paper knew this and worked hard to come up with a clever grouping strategy. These are really smart people, I know and like them very much, and they worked hard and they found a good measurement schedule deterministically. This is the blue line. The red line is our denial of service. Just randomly measure and do everything efficiently in the post-processing. And as you can see, it beats the best optimized handcrafted method at 80 qubits, which is not unthinkable of today. And the orange line is kind of our randomized measurement strategy that we now develop also together, a bit smarter. There's like tuning that it can do to improve it, and then you get this. What I want to say with this is that the task of estimating a seemingly unstructured amount of low-weight polyobservables is not an abstract problem. It happens in almost every VQE iteration that you want to do, and it happens every time you want to let the quantum computer talk to the classical computer. And in this case, an improvement from poly n to 3 to the 4 times log n, it's an exponential speedup, and you will feel it in every iteration of your quantum algorithm. So these ideas really have a place. And the cool thing is, now we all know that we can in principle trust these things because we prove that they work basically together. And I hope that this gives you confidence that we can overcome scaling issues and that we can overcome bottlenecks and really make the most out of quantum computing devices that grow larger and more exciting every year. And with that, I'm basically done. And here is my summary. Quantum hardware advances are really pushing the tried and tested techniques we've all learned to the limit of their capability. When I was young, I still learned and actively worked on quantum state tomography, which was the go-to solution to learn information about a quantum system that works for 6 qubits, that won't work for 100 qubits. And the resource scaling and all aspects of resource scaling really start to matter. We have to find solutions that are implementable on noisy hardware, that we can store on computers, and that we can actually calculate. And all these things matter. And as an example, today I started with a seemingly basic problem of estimating a collection of different polyobservables and really take a close look at it in order to make it rigorous and as scalable as possible. And in so doing, I think we succeeded. We came up with a cheap measurement design. We only needed to do single qubit rotations. This is something you can do on modern quantum architectures. And the cost is very cheap. You only need a couple of random bits for each pre-processing. The data storage is also efficient because you store bit strings and a representation of the unitary rotations unit. This is efficient because we only ever do 3. Identity Hadamard or phase times Hadamard. And the data processing is not only efficient but highly parallelizable. We can use the same data and estimate all properties in principle on different cores in order to be as fast as possible. And this is something I find very important, we also develop rigorous performance guarantees. performance guarantees that don't need the central limit theorem or a Gaussian normality approximation, but only the independence of randomness in different quantum experiments. And this is what nature gives us. And with that, I'm at the end of today's lecture. I want to remind you that this was mainly a warm-up. Next time, we will look at a similar outset, but we will look at it from the state approximation perspective rather than observable estimation as we did today. So if you wish, today we did a Heisenberg picture part of the story. We will do the Schrödinger picture part on Thursday. And until then, as I promised, this is really the easiest incarnation of a bigger vision that we'll do in the next couple of exercises. And as I promised, here are the homeworks. Plus the one by you. Can you remind the audience again what it was?
Sure, sir. Why they only need to have 1/3 choices and not 4 if it's identity X, Y, and Z?
Very good. And with that, I'm done. And I thank you for your attention. I thank you for walking this walk in probability theory with me.
So I know Paraty is waiting, but we still have time for more questions.
If they don't have, I have.
I have many, yeah.
So let me try to see if I guessed the right thing. If yes, you don't need to, but if no, try to tell me the other strategy. The randomization strategy is something like I make one choice and measure 2 polys in different places.
No. This is nothing as smart as you're suggesting because we really have near-term hardware in mind. What we actually do is there's 2 tricks for kind of like making it better. The first one is in many physical Hamiltonians, especially in quantum chemistry, X, Y, and Z terms don't have the same frequency. Like I'm not an expert, but I think in a Paraty-Susskind encoding, you don't see poly Y terms. So you should never measure the Y basis. Simple things like this. And there's efficient pre-processing strategies that bias the random Kueng in the right direction, and this gives you a lot of advantages already. What we do in the de-randomization thing is actually something smarter that I find cute, and it's a standard technique in theoretical computer science, where you start with a random suggestion and squeeze out the randomness with the promise that whatever you do, it will be better than a random choice. And so kind of what we do is we look at the very first basis of the very first qubit in the very first measurement. And then there's 3 concrete objects. We can do X, Y, or Z. And now we can see what happens if we chose to use X. How big is the probability of succeeding later on if we did everything else randomly? And we can compute the same for Y and get a different number, a different score, and we do the same for Z. And then we greedily choose the one that optimizes our success probability if we randomized everything else. And this is now an efficient strategy because we only have to compute it 3 times, pick one, and then we move to the next term. And by doing this, you really de-randomize, but keep the gist, the expected success, higher, and in practice this really pushes your success probability up. Did this answer your question?
I have 2 questions, but they probably are related.
Yes.
So the first question is about the random choice. Is it pseudo-random or how random?
Excellent question. There's many answers. Like in principle, this probability theory assumes true independent randomness, which we typically don't have. Like quantum computing is one of the few sources where we know that it works. But in practice, these tail bounds that we use, these Höfting inequalities, they are also true with weak dependencies. They become much, much harder, but you don't need true randomness. What you actually want to have is independence. It doesn't have to be perfect randomness, but you don't want your 5th choice to depend on the 3rd. It's a bit similar to like non-materiality, I guess.
This is my second question.
Yes.
Because like we assume IRG, and like if we consider like all the measurement apparatus to be perfect, then we can still assume ID, but then they introduce correlations.
Yes.
Do you work with that?
More than one answer. Okay, the first thing is, we only need to insert randomness in a measurement design stage. And this is okay. When correlations happen here, the rigorous analysis becomes harder, but people know how to do it. As for example, a recent work by Michael Walter and Johannes Kepler where they did it. And the gist is that it remains approximately the same. Here's a more empirical answer, is these tail bounds, like kind of like what you need to insert here, is a bit like in a randomized algorithm. You need a couple of independent random bits, and now you're right, kind of like we don't have independent random bits, but randomized algorithms work. So kind of like pseudo-randomness seems to be enough for these types of algorithms. Like otherwise, random search, like a lot of algorithms wouldn't work, because they use the same type of pseudo-randomness. And the last answer I want to give is that the power of this estimation really comes from the fact that the bit strings, the S strings, the bit strings, come from an actual quantum measurement. And this is where most of the randomness comes from, and where also all the expressivity comes from. And so this is not a classical randomness problem anymore, because the important part really comes from wave function collapse and the probabilistic nature of Kueng. And I need like more than 5 couple of years to discuss about whether quantum mechanics is deterministic or not.
Yeah, I think my problem more so lies in the realization of this measurement, because like this S string probably are correlated, because it's okay.
I don't think so.
So it's not time shot measurement.
No, not at all.
Okay.
It's
Okay,
like
okay.
reset and restart.
Yeah, okay.
Really. Thanks, I think this is important. This is really, we prepare a quantum system from scratch, we use pseudo-randomness to rotate, we get a bit string. There's correlation with the pseudo-randomness, but then we forget everything. We restart from scratch, build the quantum state again, and do it again with a different type of randomness. For me, this is as independent as it can get.
That makes sense.
So this is really, my T is kind of like the number of shots, and maybe it was not a smart choice in a physics audience to call it T. Nothing to do with it. We reset once we've completed the data acquisition. Thank you very much. I think this was a great point for clarification at the very end. Again, for me, I'm not a physicist, T is not time.
Last chance. Well, if not, I actually have one like so you are assuming that you are measuring X, Y, and Z like perfectly, right?
Yes.
And if you like in practice, like you're going to measure X plus epsilon Z or whatever, so you have errors every time you measure, and
Yes.
these errors might be correlated or decorrelated. So does this spoil the efficiency of the method or not really?
Excellent question, and a spoiler for the last lecture on Friday. Kind of like here's two things. In our work, we really consider these quantum systems as black boxes. So if you screwed up in your state preparation, you're on your own. We can't detect this. Okay? But what you are saying is something else. You're saying, what if I make mistakes here? And here, and this is actually a beautiful gimmick of this method, randomization helps you. Because you either measure the X, Y, or Z basis, and if you have, for example, any type of single qubit noise here, it would depolarize it. Because you measure in mutually unbiased cases. This is what people, for example, do if they do randomized benchmarking or randomized compiling. You randomly change your basis in order to turn your nasty noise into a depolarizing noise. And if you only have single qubit errors, then the depolarizing noise hits here, 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 and here, and it hits independently. And it's not difficult for you to do a calibration stage to learn it, and then undo it in the classical post-processing stage. So this actually comes with a built-in natural error mitigation technique. And if you have correlated errors, then the situation becomes a bit more complicated, but these randomizations still twirl the arbitrary noise into a Pauli channel, much like what randomized compiling would do. So randomization really helps in this regard as well. We'll talk more about this on Friday.
let's thank Ishud again for the great talk. So someone gave this cable. It was lost in the bus from São Paulo. So if you lost your cable, we see you. Okay.